Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, lesson 7, bacteria and exponential growth. Wait, what? Look at that. Just like math. It's all Greek to me. All right, lesson 7. Classwork opening exercise. Work with your partner or in groups to solve each of the following equations for x. All right, so here we go. So it's 2 to the x. It's an exponential function. So if I put x in a table over here, it might help to have a table. And then I put 2 to the x over here. Then if x is 0, 2 to the 0, anything to the 0 power is 1. If I let x be 1, 2 to the first power is 2. 2 squared, 4. 2 cubed is 8. 2 to the 4th is 16. 2 to the 5th is 32. 2 to the 6th is 64. And I see 64s here, and that's the largest number I see in these equations. So I'm going to stop right there, and this will refer to this table for these values. Okay. So if I have 2 to the power of x equals 2 to the 3rd, what would x have to be? Well, 2 to the 3rd is 8. So 2 to the what power would equal 8? Well, it's obvious that this is going to be x equals 3. And I'm just going to say it now. We've done it before. Math 7, Math 8, somewhere around there. If your bases are the same, then your powers have to be the same. So if I have a base 2 and a base 2, and this is x, and this is 3, well, no, the only way that these can be equal is if x is 3. There's no other number that's equivalent to 3. So here we have 2 to the x equals 2 to the, and if there's nothing there, it's a 1. So therefore, x has to equal 1. 2 to the 1 is 2, just like our table says. 2 to the what power equals 16? Well, it's right here. So x has to equal 4. Now we have an equation that's not just 2 to the x isolated. We are now subtracting 64. So now we have to use, and I've done this before, but I'll do it again. Okay, GEMDAS is the order of operations for expressions. SADMAG is what we do for equations because we have to do it in reverse order. So I have an exponential and I have subtraction. So what do you do first? You do subtraction first. What's the inverse of subtraction? Addition. So I'm going to add 64 to both sides. And that's going to give me 2 to the power of x equals 64. And then I look over at my table here and x has to be 6. Okay. And same here, it's again this subtraction first, add 1 to both sides. I get 2 to the x equals 1. Look familiar? It's same as b. So x has to equal 1. 2 to the first power. No, that's not true. Just kidding. 2 to the x is not equal to 2. It's equal to 1. So up here, 2 to the 0 is 1. Okay. Uh-oh. 3 times something. Okay, so here's how we're going to do this one. I'm going to get 64 down, and I want my bases to be equal. Remember what I said earlier. If your bases are the same, your exponents have to be the same. So I'm going to leave 2 to the 3x alone, and I want to make 64 2 to the power of something, and it's 2 to the 6. Now that my bases are the same, my powers have to be equal. So now it's just simply a linear equation, 3x equals 6. Divide both sides by 3, and x has to equal 2. Same with this one. 2 to the x plus 1 equals 2 to the what? Well, 32 is 2 to the 5th power, so I'm going to put a 5 here. I'm changing 32 to the same base that's on the left. And now that my bases are the same, my powers have to be equal. So x plus 1 equals 5, subtract 1 from both sides, and x must equal 4. Okay, so there's page 1. Okay, page 2 brings us to example. First example. All right, so it says the Escherichia coli bacteria, commonly known as E. coli, reproduces once every 30 minutes, meaning that a colony of E. coli can double every half hour. Mycobacterium tuberculosis has a generation time in the range of 12 to 16 hours. Researchers have found evidence that suggests certain bacteria populations living deep below the surface of the earth may grow at extremely slow rates, reproducing once every several thousand years. Wow. With this variation in bacterial growth rates, it is reasonable that we assume a 24-hour reproduction time for a hypothetical bacteria colony in this example. So we're just making up a bacteria, we're not naming it, and we're just going to say that it reproduces every 24 hours. So suppose we do have this bacteria colony that starts with one bacteria, and the population of bacteria doubles every day. What function P can we use to model the bacteria population on day T? So this is an exponential growth function. And what I want to point out here is how fast it grows. And that is the key because that tells us what our base is. So if it says doubles, our base is 2. If it says triples, our base is 3. If it says quadruples, our base is 4. Okay, so we have a base 2 exponential function here. And that is just basically 2 to the power of what's changing, which is our time. So we have P of t equals 2 doubling to the power of t time for real numbers t that are greater than or equal to 0. Okay, we're not going to deal with negative values here. We're not going to go back in time to before the one bacteria existed and where it came from and all that. We're just starting with one bacteria. So that's going to be considered ground 0 or day 0. So T2 to the 0 is 1. So we have one bacteria at the beginning. That's what this said. One bacterium. We're starting with 1. Okay. On day 1, 2 to the 1, 2 to the first power is 2. Then we're going to go on to day 2. 2 squared, we are going to have 4. It's going to double every day. So double 4 is 8, and that happened on day 3. Double 8 is 16, and that happened on day 4, and so on, and so on, and so on. Okay, so now it says, how many days will it take for the bacteria population to reach 8? Well, here's our 8. How many days was it? 3. So it is 3 days. Because 2 to the third power is 8. How many days will it take for the bacteria population to reach 16? So I'm going to do this one algebraically. I would say 2 to the t. Hello, that is not a t, it's a 6. 2 to the t equals 16. And with our rule that we used on the last page, our bases are the same. Okay. Then our powers have to be the same. So 2 to the t equals 16. I want to make 16 a base 2. And 16 is 2 to the 4th power. And now if my bases are the same, my powers must be the same. So therefore t has to equal 4. So that's doing it algebraically. So day 16, 4. Roughly how long will it take for the population to reach 10? All right, so if I were to do this one, I could say, well, 2 to the t equals 10. Uh-oh. 10 is between 8 and 16, but it's closer to 8. So how long will it take for the population to reach 10? I would say just a little bit greater than, t has to be greater than 3, but less than 4. So let me write this as a compound inequality. T is going to be greater than 3, or 3 is less than, t is less than 4. So t has to be between 3 and 4 days, but it's closer to 3. So it's early in the 3rd day or 4th day, actually. 3 days took to get to 8, and then a little bit longer will get us to 3 point something. Okay, so it's between 3 and 4 days. All right. Does that make sense? So we don't always have nice round integer numbers to work with. That's life. Okay, so anyway, we already know from our previous discussion that if 2 to the power of d equals 10, then d has to be between 3 and 4. I don't know why they switched to d, but whatever. All right, I don't know, days, I guess, but let's get rid of that, please, because there is no d in this table. It's p of t, not p of d. We already know from our previous discussion, if 2 to the t equals 10, then t is between 3 and 4, and the table confirms that. At this point, we have an underestimate of 3 and an overestimate of 4 for t. How can we find better overestimates for t? That is the question. Okay, so if you watched the prior video or were in class for lesson 6, what did we do? Okay, well, we approximated and we tried 2 to the 3.1, 2 to the 3.2, and so on. So I'm going to open my calculator up and I'm going to try that. So if I take 2 to the power of 3, I got 8. 8's less than 10. 2 to the power of 4 is 16. Whoops, I went over. Now I've got to go back to the one that's not over, 2.2 to the 3, and try 2 to the 3.1. And 2 to the 3.1 is 8.57. So what I'm going to do there is I'm just going to keep trying my 10th position until I get closer and closer to 10. So I'm going to let t equal 3.1. And p of t is 8.5742. I'm going to go out 4 decimal places. Okay, I'm going to try 2 to the power of 3.2. And that is going to be 9.189. We're not at 10 yet, so it's still an underestimate. So 3.2, p of 3.2 is 9.1896, rounding to 4. Now I'm going to try 2 to the power of 3.3. And that's going to give me 9.84. We're still not there. We're still underestimating. We're still under the actual. So it's 9.8492. And I'm going to try 3 to the 4th. So 2 to the 3.4, I mean. And that comes out to be 10.556. Okay. That's an over. So I'm going to put it here. So once I go over, I'm going to try to get more accurate here, and then I would do another table. I'm going to become really accurate here. And we are now, I think we do it on the next page though. So I'm going to stop there. I now know that my t, and I'm going to write it here, my t is now between 3.3 and 3.4. So what do I do now if I want to be really accurate? I go out to the 100th place and start with 3.31 and so on and so on and so on. All right, page 2. As I said, we're going to continue this process. From our table, we now know another set of under-over estimates for the number t. I don't know why they switched to t or d. It's p of t. It's t. I don't know. What are they? Continue this process of squeezing the number t between two numbers until you are confident you know the value of t to 2 decimal places. Okay, so here we go. So turn my calculator back on. I want 3.31, 2 to the power of 3.31, enter. 3.31 is 9.9177. 9.9177. Okay. Okay, and so we're not at 10 yet, so we're going to do the next one. 2 to the power of 3.32, enter. 9.9866. We're getting close, folks. 3.32, 9.9866. 3.866. 2 to the power of 3.33, enter. Oh, we're over. All right, we're over. 3, I'll put it here, 3.33 gave us 10.0561. Okay, and since we are now over, we want to go out to, guess what? The 100th place. Okay, so now I'm going to go back to my 3.32 and put a 1 at the end. So now I want 2.321. I now know from this table that my t is greater than 3.32, but less than 3.33. So it's 3.32, 1, 2, 3, 4, 5, 6, 7, 8, 9, somewhere in between. So we have to go out to the 100th. So 2 to the power of 2.321 is 4.9967. Actually 68. 4.9968. 2 to the power of 3. No, just kidding. I made a mistake on the last one. I put a 2 here. So disregard this. It's not 4.99. That's way too big, obviously. I wanted 3.321, enter, and it's, I'm struggling now. Start over. 2 to the power of 3.321, enter. That's better. Let me get rid of all of this. My apologies there. It is 3.321. Okay, I'm going out to the 100th on this number here, and that is 9.9936. Okay, not 10 yet. Let's keep going. 2 to the power of 3.322, enter, and we're over. Okay. So 3.322 gave us 10.0005, 1,000th over. So then we'd go out to the 1,000th position and so on, but I'm not going to. But I now know that t is greater than 3.321, but less than 3.322. So what if we wanted to find d to 5 decimal places? Well, we'd keep going, wouldn't we? Okay, well, since 3.321, and I don't know why they're using d and they have t in here, it's driving me bonkers. Okay, t has to be between 3.321 and 3.322, and both numbers round to 3.32. So we can say that d is approximately 3.32. We see that the population reaches 10 after 3.32 days. Okay, so that's what I would say. I just didn't have room. I'd say this up here. Okay, so let me just put this right here. That's the explanation above. So now let's focus on what if we wanted to find d to 5. Okay. Well, here's what we would do. Okay, we keep squeezing t. Timeout. I have to fix this. I just absolutely must change all of these to t. T. Keep squeezing t between under and over estimates until they agree to the first 5 decimal places. Note to teacher, to 5 decimal places, 3.321928. T is between those, so t is approximately this. So we're going to do that. We're going to show the process of getting that value. So it says to the nearest minimum, when does the population of bacteria become 10? So where did we leave off? We left off at 3.321. So now I want to do 3.3211. So 2 to the power of 3.3211 is 9.9947. 9.9947. And then 2 to the power of 3.3212. Enter 9.9949, or so let me see. T is 3.3212 is 9.995, rounding to this one out. Okay. So then we're going to try 2 to the power of 3.3213. Enter. Still not there. 3.3213 becomes 9.9956. Okay, continuing, 2 to the power of 3.3214. Still not there. 3.3214 is 9.9963. And now we'll do 3.3215. So it's 2 to the power of 3.3215 is, we're not there yet, 9.9970. So now I will do 3.3216. You get the idea? 2 to the power of 3.3216. Enter. Still not 10. 9.9977. 3.3217. 2 to the power of 3.3217. Still not 10. We're getting closer though. 9.9984. Now we'll do 3.3218. 2 to the power of 3.3218 is 9.9991. We are now 9/1000ths away. 3.3219. 2 to the 3.3219 is again 9.999 or 8. No, it's 9/8. All right, so guess what? We went all the way out to 19 and we didn't get to 10, but we know that 3.3212 or 3.322 was 10. So I don't want to go to that. I now have to go out to 5 decimal places, because if I now put 2 to the 3 point, now 3219, the next one would be 3.322. We know that that's, whoops, divided by. Okay, let's try that again. 2 to the power of 3.322, that'd be the next number after 19 is 20. We know that that's too big. So now I want to go 2 to the power of 3.32191. Enter. Okay, so now we're going out to 5 decimal places. 3.32191 gave me 9.9999. Getting really close here, folks. 3.32192 is the next one. So 2 to the power of 3.32192. Okay, is 9.9994. Getting close. 2 to the power of 3.32193, and we're at 10. Okay, so we're out 5 decimal places. So there is our answer, 3.32192. And I believe it stated that up here, 3.32192.893. it said first 5 decimal places, they went out 6 here. Here is our 5 decimal places, 3.32192. So I will now say T is approximately 3.32192. Okay, 3 days and almost a third of a day more, which is approximately not quite 8 hours. Okay, page 4 brings us to an exercise. Now it's your turn to practice this process. It is going to be pretty tedious, but we're solidifying something here, so be patient. Okay, so it says to use the method from the previous example to approximate the solution to the equation below to 2 decimal places. Okay, so I'm not going to do all of these because it's so tedious, because once you do a couple of them, you should be, I will do 2 of them and then I will stop. I will do something other than base 2. I will do a base 3 and I'll come down and I'll do the last one, base 16. Okay, I will do B and I will do N to show you with a process, but then I'll just give you all the answers after. But I want you to try these because practice makes perfect. So I turn the calculator on and I say, well, 3 to the x equals 1,000 and 3 squared is 9. So I'm just going to start out with the basics. I'm just going to start out with 2. 3 squared is 9. It's definitely not there. 3 cubed is 27. Remember, I want to get 1,000. 3 to the 4th power is 81. 3 to the 5th power, I feel like I'm playing 2048, is 243. 3 to the 6th power is 729. See how quick we got close to that? So I now know it's at least 3 to the 6th, but I think 3 to the 7th will be too large. And it is. So now I know it is 3 point something, or I'm sorry, 6 point something. Okay. So 3 to the 6th, it's between 3 to the 6th and 3 to the 7. That's what I'm trying to say here. So now I need to go out 1 decimal place. So I'm going to say 3 to the power of 6.1. Okay, 800 is less than 1,000. 3 to the 6.2, enter. Still under 1,000, but closer, obviously. 3 to the 6.3 is too big. So now I know it's 6.2 something. So now I'm going to go out to this 2 here, but I'm going to start out 2, 1. So I'm going to do 3 to the power of 6.21, enter. Okay. 3 to the power of 6.22, enter. Still not 1,000. 3 to the power of 6.23, enter. Getting closer. 3 to the power of 6.24, enter. Okay, getting closer. 3 to the power of 6.25, enter. Still not there. 3 to the power of 6.26, enter. 3 to the power of 6.27, enter. Still not at 1,000. 3 to the power of 6.28, enter. 991. I'm assuming if this increased by 9 and it increased by at least 9 again, it's going to go over, but I'll check. 3 to the power of 6.29 is too big. So I will stop at 0.28. Okay, but if I look back, 0.28 is 991.56. Actually, if we're gonna find the equation to 2 decimal places, I need to keep going. I need to know what the next decimal is to determine whether or not I'm going to round this. Does that make sense to you? So we do have to go out 3 decimal places and then round. So it's going to be 3 to the power of 6.281. 3 to the power of 6.282. Okay. 3 to the power of 6.283. 3 to the power of 6.284. And I'm going to do the next one differently, and I'll explain it when I get there. 3 to the power of 6.285. Enter. 3 to the power of 6.286. 3 to the power of 6.287. 3 to the power of 6.288. Whoops. Try that again. 3 to the power of 6. I missed the power button again. 6.288 is where I was. And that's too big. So this 8, I could have stopped at 5, by the way, because anything greater than 5 will round this up to 9. Okay, so that's what we were trying to figure out. So you have to go out 3 decimal places in order to round to 2. All right, so now I'm going to do n. So n is 16 to the power of something equals 1,000. So I'm going to go 16 squared, 256. 16 to the third, 4,096. See how quickly it grows when the base is bigger? 16 to the fourth, 65,000. Way too big. So I now know it is 3 point something. So I'm going to go, here's how I'm going to do this to save time. I'm going to go halfway. If I'm too big, I cut 1 through 9 in half. So I'm going to start with 0.5. You understand what I'm saying here? So I'm going to do 16 to the power of 3.5. Why do 1, 2, 3, 4, 5, 6, 7 when it's an 8? If you start at 5, if you start at 5, then you're cutting it off by half. Okay. And see right there, 3.5 is too big. So now I don't have to do 5, 6, 7, 8, 9. I know that. Now I'll try 3. And it's like a higher lower game. I'm over. Let's back up. 16 to the power of 3.3 is less than 10,000. So I now know it's 3.3. I'm pretty certain that 3.4 is going to go over. 16 to the power of 3.4 is too big. It's more than 10,000. So I'm at 3.3 something. 16 to the power of 3.3. I'm going to go up to the 5. I'm going to cut it in half. That's over 10,000. 16 to the power of 3.33. Enter. That's still too big. 16 to the power of 3.32 is my next value. 3.3 was too big. 3.2 is not big enough. Now we're going out 1 more decimal place to see if 2 gets rounded up or truncated. So I'm going to say 16 to the power of 3.32. I'm going to start in the middle between 1 and 9. And see that? 5 was too big. So I now know it's 4 or less, which will not round this up. So there's the answer, 3.32. Okay. Okay, so if you did all of these, here are the answers. A is 9 point approximately. These are all approximations. 9.97. C, 4.98. B, we did 6.29. That's why I skipped it. D, 4.29. E, 3.86. F, 3.55. Notice as the bases get larger, the number that we take the power of, or the exponent, is smaller to get to 1,000. They're decreasing. And then we get 3.32 for 8. 9 is excuse me, H is 3.14. So there I was like, well, I know a number, 3.14159 is pi. So I decided to try 2 to the pi, and notice that 0.82 is closer than 0.81 to whoops, not 2. What am I doing? So if I do 9 to the 3.14, which is what they did, we get 991.56. Now if I take 9 to the power of pi, whoops, I forgot my power. 9 to the power of 3.14, enter. 9 to the power of pi, I get 9.95. It is not 10 yet, or 1,000. So pi is a better approximation than 3.14, so that's why I wrote that there. And I see there's an error here because that went larger, so I'm going to address that in a moment. So 11 is approximately 2.88, 2.78, 2.69, 2.62, 2.55. This is not right. I'm going to do it again. 16 to the power of 2 is 256. 16 to the power of 3 is 4,000. 16 was 15 to the power of 2.55. 997. Oh, I was thinking 10,000. That's why. Ay, caramba. Okay, so that's not right. It is 2. So I will do this one again. My apologies for this error. Okay, that's why it's always good to check your answers and look at patterns. So this has to be 2 point something. So 16 to the power of 2.5 is more than 1,000. 16 to the power of 2.4 is less than 1,000. So I'm at 2.4 now. 16 to the power of 2.45, I always go in the middle, is not 1,000, so it's more than that. So that's going to be 16 to the power of 2.47. I'll skip one just to see if I go over, and I didn't. 16 to the power of 2.48. Still not. 16 to the power of 2.49. Okay, so it is going to be 2.49 something. I know 2.5 was too big. So now I'm going to go out one more decimal to see where it rounds. 16 to the power of 2.495. Enter. And that's too big. So I know it's less than 495, so it will not round up. So my answer is approximately 2.49. Sorry for that error. All right, page 5 brings us to the end of lesson 7. There are better ways to do this. This is just to get you familiar with exponential functions. And now go to your problem set.